What if everything you've been taught about the universe is wrong? What if the one constant we've relied on for over a century, the speed of light, isn't constant at all? Right now, as you're watching this, photons are streaming through space at exactly 299,792,458 meters per second. Not 299,792,457. Not 299,792,459. Exactly that number. It's been the same since the Big Bang. It's been the same in every laboratory experiment. It's the cosmic speed limit, the universal constant, the foundation of Einstein's relativity. But here's what will shatter your understanding of reality. There's no fundamental law of physics that says light has to move at this speed. We've just observed that it does. We've built our entire understanding of space, time, energy, and matter on this observation. And what I'm about to reveal to you will make you question whether we've been living in a cosmic illusion. In the next few hours, I'm going to take you on a journey that will fundamentally change how you see reality. We're going to explore what would happen if light could accelerate, if photons could speed up or slow down like everything else in the universe. And the implications are so staggering, so mind-bending, that by the end of this video, you won't be able to look at the world the same way again. But before we dive into this rabbit hole, I need you to do something. Smash that like button right now, hit subscribe, and turn on notifications, because this is the kind of content that algorithms don't want you to see. And I'm curious, drop a comment telling me what country you're watching from and what time it is there right now. Are you watching this at 2 a.m.? Unable to sleep because your mind is hungry for knowledge? Are you on your lunch break, ready to have your world turned upside down? Let me know. Because what we're about to explore together isn't just theoretical physics. It's a journey that will reveal why reality behaves the way it does, why time flows forward, why you can remember the past but not the future, and ultimately, why you exist at all. Let me take you back to 1887. Two scientists named Albert Michelson and Edward Morley were about to accidentally discover something that would break physics. They were trying to measure something called the luminiferous ether, this invisible substance that scientists believed filled all of space and allowed light to travel through it, like sound traveling through air. Everyone knew it had to exist. The logic was simple. Waves need a medium. Sound needs air. Water waves need water. Light waves must need something. So Michelson and Morley built an incredibly precise instrument called an interferometer. Their plan was brilliant. If the Earth is moving through this ether as it orbits the sun, then light should move faster when traveling with the ether's flow and slower when traveling against it, just like a swimmer moving with or against a current. They measured, they calculated, they checked their instruments, and they found nothing, absolutely nothing. Light moved at the same speed in every direction, regardless of its motion. It was as if they had measured the speed of a river and found it flowing at the same rate upstream and downstream. The scientific community was baffled. Some thought the experiment was flawed. Others proposed increasingly bizarre explanations. But one young patent clerk in Switzerland named Albert Einstein looked at these results and had a revolutionary thought. What if light doesn't need a medium at all? What if its speed is simply a fundamental property of the universe itself? In 1905, Einstein published his special theory of relativity, and here's what will blow your mind. He didn't just explain why light's speed was constant. He used that constant speed to completely rewrite our understanding of space and time. Think of it like this. Imagine you've been playing a video game your whole life, where you assumed the screen was the fixed background and the characters moved across it. Einstein essentially said, no, the character's speed is fixed, and the screen itself bends and stretches to accommodate that. This is where things get wild. Einstein showed that light's constant speed means that time itself is flexible. If you're moving near the speed of light, time slows down for you. Space contracts, mass increases. The faster you go, the slower your clock ticks relative to someone standing still. This isn't science fiction, we've measured it. Atomic clocks on airplanes tick slower than identical clocks on the ground. GPS satellites have to account for relativistic time dilation, or they'd be off by miles every single day. But here's the key insight that most people miss. Einstein didn't prove that light must move at this constant speed. He built a framework that assumes it does, and that framework makes incredibly accurate predictions. His equations have been tested billions of times. They've never failed. Black holes, gravitational waves, time dilation, mass energy equivalence, all of it flows from the assumption that light's speed is constant. Now, let me introduce you to a physicist named João Magueo. In 1998, this Portuguese cosmologist at Imperial College London did something that many considered career suicide. He proposed that light's speed might have been different in the early universe. His colleagues thought he was crazy. Students whispered in hallways. Journal editors were skeptical. But Magueo had noticed something troubling about the Big Bang theory. It's called the horizon problem, and here's why it should bother you too. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that the temperature is almost perfectly uniform across the entire sky. It varies by only about 1 part in 100,000. Here's the problem. Different regions of the sky are so far apart that light hasn't had enough time since the Big Bang to travel between them. They're causally disconnected. They shouldn't know about each other's temperature. It's like finding two isolated civilizations on opposite sides of the Earth, speaking the exact same language, with the exact same grammar and vocabulary, despite never having contact. How is this possible? The mainstream solution is called cosmic inflation, the idea that space itself expanded faster than light for a brief moment after the Big Bang, allowing everything to homogenize before expanding apart. But Magueo asked a different question. What if, instead of space expanding faster than light, light itself was moving faster in those early moments? This is where your journey into the impossible truly begins. Because if light's speed could change then, what's stopping it from changing now? And if it could change, what would that mean for everything we think we know? Imagine you wake up tomorrow and discover that the definition of an inch has changed. Not just on paper, but physically. Every inch is now 1.1 inches long. Your height hasn't changed in how many inches you are, but you're taller in absolute terms. Your car is longer. Your house is bigger. But so is everything else, including your measuring stick. So how would you even know the change happened? This is the philosophical nightmare we face when we consider a variable speed of light. And here's what's going to bend your brain. We might not be able to detect it happening even if it were. Let me explain through the work of another brilliant physicist named John Barrow at Cambridge University. In 2001, Barrow worked with Magueo to develop a mathematical framework for how a varying speed of light could actually work without destroying the universe. What they discovered was profound and terrifying. Here's the issue. Light speed isn't just a random number. It's connected to two other fundamental constants through a simple equation. The speed of light equals 1 divided by the square root of two numbers, the electric constant and the magnetic constant. These constants tell us how strong electric and magnetic fields are in empty space. So if light's speed changes, at least one of these other constants must change too. Think of it like a tripod. If one leg gets longer, the others have to adjust or the whole thing tips over. And these constants determine how atoms bond, how chemistry works, how energy flows through matter. Change light's speed, and you change everything. Let's walk through what would happen, step by step, if light could accelerate. Not over cosmic timescales, but right now, in real time. Buckle up. First, causality itself would become negotiable. Right now, the speed of light determines the structure of cause and effect. An event can only influence another event if light has time to travel between them. This creates what physicists call light cones, a geometric representation of what can affect what. If you could send a signal faster than light, you could, in principle, send messages backward in time to your past self. Not metaphorically, actually. Here's a thought experiment developed by physicist Albert Einstein himself. Though most people don't know it, imagine two spaceships passing each other at nearly the speed of light. You're on one ship, your friend is on the other. You both have powerful laser guns. From your perspective, you fire your laser first, and it hits your friend's ship. But from your friend's perspective, Y fired first, and their laser hit your ship first. Both of you are right, according to the laws of relativity. Now here's where it gets insane. If your laser could travel faster than light, there would be reference frames where your friend could receive the laser before you fired it. They could then fire their laser faster than light back at you, and it would arrive before you fired your original shot. Effect precedes cause. Time travel becomes possible. The universe doesn't just dislike this, it violently prohibits it. The constant speed of light is what protects causality. It's the scaffolding that holds the timeline together. But let's say the universe finds a way around this. Let's say light can accelerate while preserving causality somehow. What happens next? Energy and mass would lose their fixed relationship. Right now, Einstein's famous equation E equals mc tells us that energy equals mass times the speed of light squared. That little c is doing enormous work. It's why a tiny amount of mass can release tremendous energy, like in nuclear reactions. Your body contains enough mass energy equivalent to several nuclear bombs. The only reason you're not exploding is that converting mass to energy is extremely difficult. But if c isn't constant, then neither is the exchange rate between mass and energy. Imagine an economy where the value of money changed from second to second. $1 could buy a coffee one moment and a car the next. That's what would happen to mass energy conversion. The sun, which produces energy by converting mass to energy in its core, would become unstable. Stars across the universe would flicker like dying light bulbs. Some would explode. Others would collapse. Here's something that will make you pause. Your own body runs on mass energy conversion. The ATP molecules that power your muscles, your thoughts, your heartbeat, they're converting chemical potential energy with efficiencies determined by fundamental constants. If light speed varied, you might not be able to metabolize food properly. Your neurons might not fire correctly. Reality itself would become hostile to life as we know it. Now let's talk about atoms. Every atom is a delicate balance of forces. Electrons orbit nuclei because of the electromagnetic force. The nucleus holds together because of the strong nuclear force. These forces have specific strengths, and those strengths depend on fundamental constants, including the speed of light. In 1999, a team of astronomers led by John Webb analyzed light from distant quasars' light that had been traveling for billions of years. They measured something called the fine structure constant, which determines the strength of electromagnetic interactions. And they found something shocking. The constant appeared to be slightly different in the distant past. It was only a difference of a few parts per million, but it was statistically significant. If true, this means the strength of electromagnetism has changed over cosmic history. And since the fine structure constant includes the speed of light in its formula, this hints that light's speed might have changed too. This discovery was controversial. Other teams couldn't replicate it. Some found errors in the analysis. Others found confirming evidence. The debate still rages today, but the mere possibility that fundamental constants could vary has opened a door that cannot be closed. What if I told you that the speed of light might be like the temperature of a room stable most of the time, but capable of changing under the right conditions? Now we need to dive into something that's going to completely shift your perspective. Everything I've told you so far assumes light is a wave moving through space. But that's not the whole story, not even close. Light is also a particle. Or rather, it's both, or neither. Welcome to quantum mechanics, where reality stops making sense and starts making a different, weirder kind of sense. Let me introduce you to photons, particles of light. Each photon is a discrete packet of electromagnetic energy with no mass, no electric charge, and no expiration date. A photon emitted from a star on the other side of the universe billions of years ago arrives at your eye in essentially the same state it started. It doesn't age. It doesn't decay. From the photon's perspective, if it had one, no time passes during its journey because at the speed of light, time dilation is infinite. But here's where things get strange. Photons aren't really traveling in the way you think they are. When a photon moves from point A to point B, quantum mechanics tells us that it actually takes every possible path simultaneously. It goes straight. It curves left. It curves right. It loops around. It zigzags. All at once. This isn't metaphorical. In 1948, physicist Richard Feynman developed a mathematical framework called the sum over histories, or path integral formulation of quantum mechanics. He won a Nobel Prize for it in 1965. His equations show that to calculate where a photon will end up, you have to add up the contributions from literally every possible path it could take, no matter how absurd. Now, here's what's going to blow your mind. What if different paths have different effective speeds? Think about it like this. Imagine you're walking from your house to a store 1 mile away. The straight path takes you 20 minutes. But there are infinite other paths you could walk in circles, zigzag, loop around. Some paths might be 10 miles long and take you 3 hours. In classical physics, you'd pick the fastest route. In quantum mechanics, you simultaneously take all routes, and they somehow interfere with each other to produce the final result. For photons, most of these paths cancel out due to quantum interference, and what remains is the path that takes the shortest time, according to a principle called the least action. This is why light appears to travel in straight lines and at a constant speed. It's not that it is traveling that way. It's that all the other possibilities cancel out. But what if they didn't cancel perfectly? What if, under certain conditions, some of those alternative paths contributed more than they should? The photon would appear to move faster or slower than the usual speed of light, not because it's actually accelerating, but because it's taking a different quantum path. This isn't just speculation. In 2011, physicists at the University of Hong Kong demonstrated something remarkable. They used a clever experimental setup to show that a photon could appear to arrive at a destination before a photon, traveling the normal route, making it seem like the photon had traveled faster than light. They called these superluminal photons. Now, before you get too excited, the physicists were careful to point out that this doesn't allow faster-than-light communication or time travel. No information actually traveled faster than light. It was a quirk of quantum mechanics. The photon was taking advantage of quantum tunneling and interference to effectively skip ahead in a way that doesn't violate causality, but it does prove something profound. The speed of light isn't quite as absolute as we thought. Even in our current universe, there are quantum loopholes. There are edge cases. There are situations where photons behave in ways that seem to bend the rules. Let's go deeper. In 2000, physicist Gunter Nimms in Germany claimed to have transmitted Mozart's 40th Symphony at speeds faster than light using quantum tunneling through a barrier. Other photons, control photons that went around the barrier, took longer to arrive. The tunneled photons appeared to arrive first, suggesting they had traveled faster than light through the barrier. The physics community had a field day with this. Some said it was real faster-than-light transmission. Others said it was an illusion of measurement, that no actual information was traveling faster than light. Just as you can make the spot of a laser pointer sweep across the moon faster than light without any actual thing moving that fast. But here's the question that should haunt you. If quantum mechanics allows these apparent violations, even if they don't transmit information, what does that tell us about the nature of light's speed? Is it really a speed limit, or is it more like a statistical average of quantum possibilities? Imagine you're told that cars on a highway have a speed limit of 65 miles per hour. But then you discover that, due to quantum mechanics, cars are actually taking every possible path and speed simultaneously. And 65 miles per hour is just the average that emerges when you measure them. Some quantum versions of the car are going 100 miles per hour. Some are going 30 miles per hour. Some are going backward in time. They all cancel out to produce the observed 65 miles per hour. Would you still call 65 miles per hour a speed limit? Or is it just a statistical artifact? This is the question at the heart of whether light can truly accelerate. Maybe it already is accelerating and decelerating wildly at the quantum level, and we only see the average. Maybe the constant speed of light is an emergent property something that appears constant at large scales, but breaks down when you look closely enough. And here's the kicker. If light speed is an emergent property rather than a fundamental one, then there might be conditions, extreme conditions, but conditions nonetheless, where the emergence breaks down and the underlying quantum chaos shows through. What would those conditions be? That's what we're about to explore, and it's going to take us to the edge of black holes, the beginning of time, and the far future of the universe. Let me take you to the most extreme environment in the known universe, the event horizon of a black hole. Specifically, let's visit Sagittarius A*, the supermassive black hole at the center of our Milky Way galaxy. It's about 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. At the event horizon, the point of no return, something impossible happens. Light, which always moves at 299,792,458 meters per second, finds itself frozen in place. Not slowed down, frozen. A photon sitting exactly at the event horizon is moving at full light speed, but making no progress outward. It's like running on a treadmill at full sprint, but staying in the same spot. How is this possible? Einstein's general relativity explains it like this. Gravity isn't a force pulling on things. It's the curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects follow the straightest possible paths through this curved geometry. Near a black hole, space-time is bent so severely that even the straightest possible path for light leads inward. But here's what's going to break your brain. From the photon's perspective, nothing changes. It's still moving at light speed. It's still following a straight line. But from the outside, it appears frozen because the geometry of space-time itself has become so warped that forward no longer means away from the black hole. Now, let's do a thought experiment. Imagine you could somehow give that photon a little extra push. Not by applying a force. Photons are massless and don't experience force the way massive particles do. But what if you could inject extra energy into it while it's sitting at the event horizon? What if you could make it accelerate? In our normal understanding, this is impossible. A photon always moves at light speed in vacuum, regardless of its energy. Higher energy photons, like gamma rays, don't move faster than lower energy photons, like radio waves. They just have shorter wavelengths and higher frequencies. Energy and speed are decoupled for light. But at the event horizon, where space-time itself is breaking down, where quantum effects and gravitational effects become equally important, where our equations literally divide by zero and produce infinities, maybe, just maybe, the normal rules don't apply. This is the domain of quantum gravity, the holy grail of theoretical physics. We don't have a complete theory of quantum gravity yet. String theory, loop quantum gravity, causal set theory, These are all attempts to merge quantum mechanics with general relativity, and they all predict weird things happening at extreme scales. Some versions of quantum gravity suggest that space-time itself isn't continuous, but is made of discrete chunks, like pixels on a screen. If that's true, then the speed of light might be limited by how fast information can hop from one pixel to the next. In normal, flat spacetime, this speed is constant. But in curved spacetime, or in the early universe, when spacetime itself was in a different state, the pixel size might have been different, allowing light to move faster or slower. Let me introduce you to physicist Stephen Carlip at UC Davis. His work on quantum gravity suggests that at the Planck scale about 10 to 35 meters, the smallest meaningful length in physics spacetime becomes foamy and chaotic. At these scales, the geometry fluctuates wildly. Space and time lose their smooth, continuous nature. Cause and effect become fuzzy. In this quantum foam, light doesn't travel smoothly. It hops erratically between fluctuating geometric configurations. On average, over large distances, this produces the constant speed we observe. But locally, at any given instant, a photon might be moving faster or slower depending on the local structure of the quantum foam. Think of it like this. Imagine you're watching someone walk across a field from far away. They appear to move at a steady pace. But if you had a microscope showing their individual steps, you'd see that each step varies in length and speed. Sometimes they step on a rock and slow down. Sometimes they step off a curb and speed up. The average is constant, but the instantaneous speed is anything but. Now let's shift to another extreme environment, the Big Bang itself. In the first y-43 seconds after the universe began the Planck epoch, entire observable universe was smaller than a proton. The energy density was so extreme that all four fundamental forces, gravity, electromagnetism, strong nuclear, weak nuclear, were unified into a single superforce. In this environment, the fundamental constants we know today hadn't frozen out yet. They were in a symmetric, high-energy state. Light's speed, as we understand it, might not have existed as a concept yet. Instead, there was just undifferentiated energy sloshing around in a space so small and hot that quantum effects dominated everything. As the universe expanded and cooled, there was a series of phase transitions moments when the laws of physics literally changed as forces separated out and particles acquired properties. The first phase transition happened around y-36 seconds, when gravity separated from the other forces. The next happened around 10 to 12 seconds, when the strong nuclear force separated. What if, during these phase transitions, light's speed changed? What if the constant we measure today is just the frozen value that happened to emerge when the universe cooled below a certain critical temperature? To understand this, think about water. Above 100 degrees Celsius, water is a gas. Below 0 degrees Celsius, it's a solid. Between those temperatures, it's a liquid. The properties of water, its density, its ability to dissolve things, its surface tension, are completely different in each phase. But it's all still H2O molecules. The fundamental building blocks are the same. Only their arrangement and behavior change. What if light's speed is like the density of water, a temperature-dependent property that seems constant only because we live in a universe that has cooled to a specific temperature and hasn't changed much in billions of years? Here's where the story gets even stranger. There are hypothetical particles called tachyons that always move faster than light. They're not just fast. They can only exist at speeds above light speed. If they slowed down to light speed, they would require infinite energy, the reverse of how normal particles would require infinite energy to speed up to light speed. Tachyons have never been observed, and most physicists think they don't exist because they cause all sorts of logical problems, like allowing time travel. But mathematically, they're allowed by relativity. The equations don't forbid them. They just described their weird properties. Now imagine this. What if photons and tachyons are two sides of the same coin? What if particles of light can exist in two phases? A slow phase, where they move at the speed we call c, and a fast phase, where they move faster. The transition between phases would require crossing an energy barrier or encountering specific environmental conditions, like the phase transition between water and steam. In most of the universe, photons are stuck in the slow phase because that's the energetically favorable state. But in extreme environments near black holes, in the early universe, or perhaps in the far future, when the universe's properties have evolved, photons might be able to transition to the fast phase and become tachyonic. This isn't just wild speculation. In 2012, physicists at CERN announced they had detected neutrinos traveling faster than light. They later retracted this due to an equipment error, but the initial excitement reveals how seriously scientists take these possibilities. The point is, even mainstream physics acknowledges that we're working with incomplete theories and that surprises are possible. So what would happen if light could accelerate in these extreme environments? Let me paint you a picture that will change how you see the universe forever. Imagine standing at the edge of a black hole safely far away, but close enough to see the event horizon. You're watching photons trying to escape. Most fall back in, but every once in a while, conditions align just right. Quantum fluctuations in the spacetime foam create a tiny corridor, a brief window of reduced curvature. A photon accelerates just for an instant and shoots outward faster than it should be able to. From the outside, you'd never notice. The photon still reaches you at the speed you expect, but something has changed. That photon has tasted acceleration. It's carried information about a regime where light speed isn't constant. It's proof that the rules can bend. Now zoom out, way out. Look at the universe as a whole. Right now, space itself is expanding, and that expansion is accelerating. We discovered this in 1998 through observations of distant supernova by teams led by Saul Perlmutter, Brian Schmidt, and Adam Riess. They won the Nobel Prize in 2011 for this. Galaxies are moving away from each other faster and faster, driven by something we call dark energy. Here's what most people miss. Dark energy is described as a property of space itself. It's not a substance or a force in the traditional sense. It's a fundamental feature of the vacuum-empty space has energy, and that energy causes space to expand. The equations that describe this are the same equations that connect light speed to the properties of empty space. So here's the question that should terrify and excite you. If the properties of empty space are changing as dark energy accelerates the universe's expansion, could light speed be changing too? Let's think about what this would mean. Imagine you measure the speed of light today and get 299,792,458 meters per second. Then you measure it again 1 billion years from now and get 299,792,460 meters per second. An increase of just 2 meters per second. Completely undetectable, given the limitations of our measurements and the short span of human observation. But over cosmic timescales, this would accumulate. Light emitted from distant galaxies billions of years ago would have been traveling at a slightly different speed than light travels today. When we measure the properties of that ancient light, its redshift, its energy, the way it interacted with matter along its journey, we'd get results that don't quite match our current theories. And here's the thing, we're already seeing anomalies. The Hubble tension is one of the biggest unsolved problems in cosmology. When we measure the expansion rate of the universe using light from the early universe, a cosmic microwave background, we get one number. When we measure it using light from relatively nearby supernova, we get a different number. They disagree by about 9% way more than can be explained by measurement errors. Cosmologists have proposed dozens of explanations. Maybe dark energy is evolving. Maybe our model of the early universe is wrong. Maybe there's an unknown type of matter or energy affecting the measurements. But what if the answer is simpler and more radical? What if light speed was different in the early universe? João Magueo and John Barrow's varying speed of light theories were specifically designed to address cosmological problems like this. If light moved faster in the early universe, it would explain the horizon problem I mentioned earlier without needing cosmic inflation. It would also potentially resolve the Hubble tension if light speed has been gradually decreasing as the universe ages. But let me take you somewhere even more mind-bending. What if light speed doesn't just vary over time? What if it varies with direction? This idea is called cosmological birefringence, or anisotropic light propagation, and it's exactly what it sounds like. Light might travel at different speeds depending on which direction it's going. The universe might have a preferred direction built into its fabric, like wood grain in a piece of lumber. In 2016, a team analyzing data from the European Space Agency's Planck satellite found hints of such a preferred direction in the cosmic microwave background. The pattern of tiny temperature fluctuations wasn't perfectly symmetric. There seemed to be a subtle alignment with a particular axis through the universe, sometimes called the axis of evil, not because it's malevolent, but because it shouldn't exist according to our theories. If this is real, it means the universe isn't perfectly isotropic. And if the universe has directionality built in at a fundamental level, then physical constants including light speed might vary depending on that direction. Think about what this means. Light from some galaxies would arrive at Earth having traveled slightly faster than light from other galaxies. Not because the galaxies are in different types of space, but because the path between us and them is aligned differently with the universe's hidden grain. This would rewrite cosmology. Distance measurements to galaxies would need to be recalculated. The age of the universe might be different than we think. The rate of structure formation, how galaxies and galaxy clusters formed, would need new models. Everything we think we know about cosmic history would be called into question. Now, let me show you where this gets really wild. Let's fast forward to the far future of the universe trillions upon trillions of years from now. The expansion has continued accelerating. Galaxies have moved so far apart that they're beyond each other's cosmic horizons. Each galaxy is alone in an observable universe that contains only itself. In this era, called the heat death or Big Freeze, the universe has reached maximum entropy. Stars have burned out. Black holes have evaporated through Hawking radiation. All that's left is a thin soup of photons and other massless particles, spread so thinly that the average temperature is approaching absolute zero. In this environment, something strange might happen. Without matter, without energy density, without structure, the properties of spacetime might drift. Constants that seemed fixed might relax into new values. Light speed might increase as the fabric of space becomes ever more stretched and tenuous. Imagine a photon in this far future. It's essentially alone, traveling through nearly empty space for distances measured in trillions of light years. There's nothing to interact with, nothing to anchor it to the speed we know today. What if, gradually, imperceptibly, it begins to move faster? Not because anything is pushing it, but because the resistance of space-time itself has faded? And here's the truly mind-bending possibility. What if this faster light loops back around? What if the universe's geometry, shaped by its expansion history, creates paths where these accelerated photons from the far future re-enter the past? Not through time travel in the traditional sense, but through the topology of an eternally expanding space-time? This is pure speculation, but it's grounded in real physics. General relativity allows for closed time-like curves paths through space-time that loop back on themselves. They require exotic conditions, like rotating universes or traversable wormholes, but they're mathematically consistent. If light speed varies in different epochs of cosmic history, it might enable temporal connections that are currently impossible. And if that's true, then the universe isn't just evolving forward in time. It's connected to its own past and future through light that has learned to accelerate. Here's a question that's going to make you uncomfortable. If light speed changed, how would we measure it? Think carefully about this. Every clock we've ever built relies on counting periodic processes. Atomic clocks count the oscillations of cesium atoms. Mechanical clocks count the swings of a pendulum or the vibrations of a quartz crystal. Even your perception of time, your sense of how fast seconds pass, is based on neural processes that have characteristic rates. But all of these processes ultimately depend on the speed of light. Atomic oscillations involve electrons orbiting nuclei, held in place by electromagnetic forces that propagate at light speed. Chemical reactions involve the breaking and forming of bonds, which are electromagnetic in nature. Even gravity waves propagate at light speed according to Einstein's theory, confirmed in 2015 by LIGO's detection of gravitational waves from merging black holes. So if light speed changed, wouldn't all our clocks change proportionally? If light suddenly moved twice as fast, electromagnetic interactions would happen twice as fast. Atoms would oscillate twice as quickly, and our atomic clocks would tick twice as fast. We'd measure light's new speed using our new clocks and get the same answer. This is what physicists call the conspiracy of constants. Light speed, the charge of the electron, the strength of gravity, these constants are all interconnected. Change one, and others must change to maintain consistency. And because we measure everything in terms of these same constants, the changes might cancel out in our measurements. It's like trying to measure the size of a room using a ruler, but every time the room expands, the ruler expands proportionally. You'd always measure the same dimensions, even though the true size is changing. But here's the loophole, and this is crucial. Not all physical processes depend on these constants in the same way. Some processes are more sensitive to light speed than others. If light speed changed, different types of measurements would shift by different amounts. The ratios between them would change, and that's what we detect. Let me give you a concrete example. In 1999, astronomer John Webb analyzed light from distant quasars, the bright cores of galaxies powered by supermassive black holes. This light had traveled for billions of years before reaching Earth. Along the way, it passed through clouds of gas that absorbed specific wavelengths of light, creating absorption lines in the spectrum. Webb measured these absorption lines and compared them to absorption lines created by the same elements in laboratory experiments here on Earth. He found something shocking. The spacing between the lines was slightly different. The pattern was shifted in a way that suggested the fine structure constant at sea, which involves light speed, had a different value in the distant past. The difference was tiny, about 6 parts per million, but it was consistent across many quasars at different distances, and it pointed in a specific direction. The fine structure constant was smaller in the past, which could mean light was moving faster back then. Other teams tried to replicate Webb's findings. Some found similar results. Others found no variation. Some found variation in the opposite direction. The debate is still ongoing, and the consensus is that if the variation exists, it's right at the edge of what we can measure, maddeningly close to the threshold of detection. But let's assume for a moment that the variation is real. How would we confirm it definitively? We'd need to measure light speed using methods that don't rely on electromagnetic processes. And that's incredibly difficult because, as I mentioned, almost all our clocks and rulers ultimately depend on electromagnetism. However, there is one force that's different: gravity. Gravitational interactions don't propagate through electromagnetism. They're a separate fundamental force, and in Einstein's theory, they propagate at the speed of light. But this is a separate fact that doesn't depend on the electromagnetic properties of light. So here's a way to detect a varying speed of light. Compare the speed of light to the speed of gravitational waves. If they're always exactly equal, That supports Einstein's unified picture. If they diverge, even slightly, that would be revolutionary. In 2017, we got our first chance to do exactly this test. LIGO detected gravitational waves from two neutron stars colliding 130 million light-years away. Just 1.7 seconds later, gamma-ray telescopes detected light from the same collision. Given that the signals traveled for 130 million years, arriving within 1.7 seconds of each other means the speeds are equal to within 1 part in 1015, an incredibly precise measurement. This ruled out many theories where light speed differs significantly from gravitational wave speed. But it didn't rule out small variations, or variations that affect both equally. The game continues. Now, let me show you another approach, looking for variations in light speed across different wavelengths. Remember, in quantum mechanics, photons come in different energies. Radio photons have low energy. Gamma-ray photons have high energy. In normal physics, they all travel at the same speed in vacuum. But in some quantum gravity theories, the structure of spacetime at the Planck scale could cause high-energy photons to travel slightly slower than low-energy photons, sort of like how light travels at different speeds through glass, depending on its wavelength. This is why prisms split white light into rainbows. In 2009, NASA's Fermi Gamma-Ray Space Telescope observed a massive gamma-ray burst from a galaxy 7.3 billion light-years away. The burst emitted photons with a wide range of energies. If high-energy photons traveled slower due to quantum gravity effects, they would arrive slightly later than low-energy photons, even though they were emitted simultaneously. The Fermi team measured the arrival times with incredible precision. They found no difference. This ruled out certain quantum gravity models and placed tight constraints on how much light speed could vary with energy. But again, it didn't rule out all possibilities, only certain extreme ones. Here's what you need to understand. Physics is a game of increasingly precise measurements chasing increasingly subtle effects. Every time we improve our instruments, we discover new layers of reality. Atoms were once considered fundamental and indivisible. Then we discovered electrons, protons, and neutrons. Then quarks and leptons. Then we found hints of substructure in those. Each layer seemed final until we looked closer. We might be in a similar situation with light speed. Our current measurements are precise to about 15 decimal places. That's astonishingly good. But what if the variation is in the 16th decimal place? Or the 20th? What if it only manifests in conditions we haven't yet created or observed? Even higher energies, even stronger gravitational fields, even stranger quantum states. And here's the truly unsettling thought. What if the variation is happening right now, all around us, but in a way that's perfectly calibrated to cancel out in all our measurements? What if there's a cosmic conspiracy not to hide the truth, but simply because the universe's laws are structured such that certain things are unobservable from within the system? Think about shadows. You can see an object and its shadow, but the shadow can never see itself. It has no perspective from which to observe its own existence. What if we're like shadows, trying to measure properties of the light that creates us, fundamentally limited by our nature as observers within the system? This is the measurement problem at its most profound, and it's why the question of whether light can accelerate might not have a simple yes or no answer. The answer might be yes, but in ways that are fundamentally hidden from us. Or no, but for reasons we can't prove because proving them would require accessing information outside our observable universe. Or maybe, just maybe, we're on the verge of a breakthrough that will crack this open. And that possibility should absolutely thrill you. Let's take a sharp turn now and ask a practical question. If we could control light's speed, if we could make photons accelerate or decelerate at will, what could we do with that power? First, let's acknowledge the elephant in the room: faster-than-light communication. Imagine being able to send messages between Earth and Mars, not in the 3 to 22 minutes it currently takes, depending on planetary positions, but instantaneously. Space exploration would be revolutionized. Controlling rovers on Mars would become like playing a video game with no lag instead of giving commands and waiting 40 minutes for a round-trip confirmation. But that's just the beginning. Real-time communication across interstellar distances would become possible. We could have conversations with probes at the edge of the solar system. We could coordinate multi-planetary civilizations. The isolation of space would vanish. However, there's a catch: the causality problem I mentioned earlier. Faster-than-light signals would allow you to send messages to your own past, creating time paradoxes. You could tell yourself not to send the message in the first place, creating a logical contradiction. Most physicists believe the universe prevents this through some mechanism we don't fully understand yet. But what if there's a workaround? What if you can't send information faster than light, but you can send energy? This might sound like a useless distinction, but it's not. Energy without information is power, and power enables work. Imagine solar panels on Earth receiving light from the sun in 8 minutes, as they do now. But now imagine we have satellites near the sun that can pre-accelerate solar photons, making them arrive at Earth in, say, 4 minutes. You haven't sent information faster than light because the photons still carry the same information. They're still just electromagnetic energy from the sun. But you've increased the energy flux. More photons arriving per second means more power. Or imagine the reverse: a photon break that slows down light in a region of space. Light entering this region would get compressed, its wavelength would shift, and it would release energy as it decelerated. You could harvest that energy. Essentially, you'd be extracting energy from the light field itself, using the change in light speed as a power source. This sounds like science fiction, but remember, we already manipulate light speed in materials. Light slows down in glass, water, and diamonds. The more it slows down, the more the material's refractive index increases. Some materials, called slow light materials, can reduce light speed to just a few meters per second slower than a person walks. In 1999, physicist Lin Hao at Harvard University slowed light to 17 meters per second by passing it through a Bose-Einstein condensate, supercold cloud of atoms in a quantum state where they all act as a single entity. In 2001, she stopped light completely, storing its information in the quantum states of the atoms, and then released it later. She created what's essentially a light memory. Now, Hao's work involved light in a medium, not in vacuum. The speed of light, that's fundamental, is the vacuum speed. But here's the thing: the quantum mechanics underlying why light slows in media could potentially be engineered to work in vacuum if we understood how to structure the vacuum's quantum fields correctly. Theoretical physicists have proposed concepts like quantum metamaterials that would structure empty space itself to alter its electromagnetic properties. This is wildly speculative, but the math allows it. If you could create regions of space with different vacuum properties, light would change speed when passing between them, just like it does when moving from air to water. What could you do with this? One application: gravitational wave detectors. LIGO detects gravitational waves by measuring how they stretch and compress space, which changes the time it takes light to travel on the detector's arms. If you could amplify this effect by putting slow light regions in the detector, you'd become sensitive to even weaker gravitational waves. You could detect collisions from across the observable universe. Another application: quantum computing. Right now, quantum computers struggle with a problem called decoherence. Quantum information gets corrupted by interactions with the environment. One way to reduce this is to slow down quantum processes so they complete before decoherence sets in. If you could slow light in your quantum computer, you could slow down quantum gate operations, giving them more time to execute accurately. But let's think bigger. What if you could create an event horizon of your own by manipulating light speed? An event horizon exists where escape velocity equals light speed. But if you could locally increase light speed, imagine a spaceship that creates a bubble around itself where light moves at, say, 10 times the normal speed. From inside the bubble, the universe outside would appear to be moving in slow motion because their light takes longer to reach you. You'd be living in a fast-forward bubble while the universe outside proceeds normally. This is reminiscent of the Alcubierre drive, a theoretical faster-than-light propulsion concept proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive doesn't move the ship. Instead, it compresses space in front of the ship and expands it behind. The ship sits inside a warp bubble that surfs the wave of expanding space. From an outside observer's perspective, the ship appears to move faster than light, but locally, it's not violating any laws. The ship itself isn't moving through space faster than light. Space is moving around it. Creating an Alcubierre drive requires exotic matter with negative mass, which probably doesn't exist. But if you could manipulate light speed instead, you might achieve similar effects. Compress space by increasing local light speed. Expand it by decreasing light speed. The mathematics would be different, but the outcome effect of faster-than-light travel could be the same. Of course, the energy requirements would be astronomical. We're talking about manipulating the fundamental properties of spacetime over macroscopic regions. That's not something you do with a car battery. You'd need the energy output of stars, contained and controlled with precision. But here's where it gets interesting. Every impossibility in physics is just an engineering problem with a really high energy cost. Nuclear fusion was impossible until we figured out how to confine plasma at 100 million degrees. Antimatter production was impossible until we built particle accelerators. If varying light speed is possible in principle, then it's just a matter of scale and energy. And we might not need to control light speed directly. We might be able to harness natural variations. If light speed varies near black holes, we could use black holes as laboratories or even as engines. A sufficiently advanced civilization might position itself near a black hole's event horizon, where the weird physics of variable light speed becomes accessible, and use those effects to power technologies we can't even imagine yet. Think about that. Black holes, which we currently see as cosmic death traps, could become power plants and research stations for a civilization that understands how to work with variable light. In fact, physicist Roger Penrose proposed in 1969 that you can extract energy from a rotating black hole through a process now called the Penrose process. Drop matter into the black hole's ergosphere, a region just outside the event horizon, and under the right conditions, you can extract rotational energy from the black hole itself. A rotating black hole is essentially a giant flywheel with more stored energy than billions of stars. If we add variable light speed to the mix, the possibilities multiply. You could potentially use the region where light speed changes as a form of energy converter, translating between different forms of energy with efficiencies impossible in normal space. I know this all sounds insanely futuristic, but remember, every technology we use today would have seemed like magic a few centuries ago. The phone in your pocket can access all of human knowledge instantly that would have been considered supernatural in the year 1700. We've gone from horse-drawn carriages to space stations in 150 years. Who knows what the next 150 will bring? And here's the thing. If light can accelerate, even in principle, then these technologies shift from impossible to very difficult. And humanity has a pretty good track record with very difficult problems. Why? Be informational universe. Light as data carrier. Now, I want to take you in a completely different direction that's going to reframe everything we've discussed. Forget about photons as particles or waves for a moment. Think about light as information. Every photon carries information. It carries information about its source, what emitted it, when, from where, with what energy. It carries information about its journey, what it passed through, what absorbed some of its siblings, what scattered it. And when it reaches a detector, like your eye or a telescope, it transfers that information, adding to the total information content of the detector. In 1948, Claude Shannon, no relation to Claude the AI assistant, by the way, developed information theory, which quantifies information mathematically. One of his key insights was that information has a maximum transmission speed determined by the channel's properties. For a communications channel using light, a maximum speed is the speed of light. You can't send information faster than your carrier can travel. That seems obvious. But here's the twist. What if information itself is the fundamental thing, and the speed of light is a consequence of information theory applied to the universe? This is the perspective of it from bit, a concept championed by physicist John Wheeler. Wheeler proposed that the universe is fundamentally made of information, and all physical properties, mass, energy, spacetime itself emerge from information relationships. He summarized it with the phrase, it from bit. Otherwise put, every particle, every field of force, even the spacetime continuum itself, derives its function, its meaning, its very existence entirely from binary choices, bits. In this view, a photon isn't primarily a physical object that carries information. It is information in physical form, and its speed isn't a limit on how fast it can move, but a limit on how fast information can propagate through the network of binary relationships that constitute reality. Now, here's where your brain is going to start hurting. If the universe is fundamentally informational, then the amount of information that can exist in a region of space might be limited. This is called the holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, building on insights from black hole thermodynamics by Jacob Bekenstein and Stephen Hawking. The holographic principle says that the maximum information content of a volume of space is proportional, not to the volume, but to the area of its boundary. This is weird. It's like saying that everything inside a room can be perfectly described by information written on the room's walls, with nothing truly inside that isn't already encoded on the surface. Black holes provided the key insight. Bekenstein and Hawking discovered that a black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. This suggests that the 3D space we perceive might be a kind of projection from a 2D information surface, like a hologram appearing three-dimensional, even though the holographic film is flat. So what does this have to do with light speed? Everything. If information is fundamental, and information is bounded by area rather than volume, then the rate at which information can move through space is limited by geometric constraints. The speed of light might be the rate at which information propagates through this 2D holographic surface, with the 3D motion we observe being a projection. And if that's true, then accelerating light would really mean increasing the information transfer rate of the holographic surface. This might be possible if you could somehow add more bandwidth to a region of the holographic boundary, allowing more information to flow through. I know this sounds abstract, so let me give you an analogy. Imagine the universe is like a video game. Everything you see is rendered on your screen, which has a fixed number of pixels. Let's say 1920 by 1080. The frame rate, how many times per second the screen updates, is analogous to the speed of light. It determines how fast information, changes in the game state, can be displayed. Now, most of the time, the frame rate is constant. But sometimes, when a lot is happening on screen, the frame rate drops. The game slows down because the computer can't process information fast enough. Conversely, if you upgrade your hardware, the frame rate increases and the game runs faster. In this analogy, regions of space-time with different properties, like near black holes, might have different hardware specs, affecting the local information processing rate, the local speed of light. And just as video game developers can optimize code to run faster on the same hardware, maybe physical processes can optimize information flow to effectively exceed the usual light speed limit. This isn't just philosophy. There's real physics here. In quantum information theory, there's a concept called quantum channel capacity, the maximum rate at which quantum information can be transmitted through a system. For a quantum channel using photons, the capacity depends on the number of photons, their energy, and the noise in the system. In 2005, physicist Seth Lloyd at MIT and others calculated the ultimate physical limits on computation. They found that a 1 kilogram computer, the size of a liter, could perform at most 1,051 operations per second and hold at most 1,031 bits of memory. These limits come directly from quantum mechanics and relativity, from the speed of light, the uncertainty principle, and the structure of spacetime. But notice, these are limits for a 1 kilogram, 1 letter computer in normal spacetime. Change the properties of spacetime, and the limits change. Near a black hole, where time slows down, a computer would appear to run faster from an outside perspective, though from the computer's perspective, nothing changes. In a region where light moves faster, computational limits would increase proportionally. This suggests something profound. Intelligence and information processing are tied to the structure of spacetime. A civilization that could manipulate light speed wouldn't just be able to travel faster or communicate faster. They could think faster, process information faster, experience subjective time at accelerated rates. Imagine a computer designed to operate in a region where light moves 1,000 times faster than normal. From its perspective, it's running at normal speed. But from our perspective, it completes 1,000 times more operations in the same external time. You could upload your consciousness into such a system and experience millennia of subjective time in a single year of external time. This is the kind of technology that would emerge if light speed manipulation were possible. Not just faster ships, but faster minds. Not just quicker messages, but compressed experience. Time itself becomes malleable when light becomes variable. And here's the ultimate implication. If light speed determines the rate of information flow, and information flow determines consciousness, then changing light speed might be equivalent to changing the rate of consciousness. You wouldn't just be accelerating photons. You'd be accelerating thought itself. Some physicists and philosophers have speculated that consciousness might be tied to quantum information processing in the brain. If that's true, and if light speed variations affect quantum processes, then entering a region with different light speed might literally alter your stream of consciousness. Your thoughts might speed up or slow down. Your perception of time might shift. This brings us to a disturbing question. Is your consciousness tied to the specific value of light speed in your region of spacetime? If you traveled to a region where light moved differently, would you still be you? Or would the change in information processing rate fundamentally alter the nature of your subjective experience? These aren't just philosophical questions. They're practical concerns for any civilization that develops the technology to manipulate spacetime. And they highlight why the speed of light isn't just a number in physics equations. It's a parameter that defines the nature of reality, experience, and existence itself. P-Y. A. Multiverse angle. Different light speeds in different universes. Let us step even further back and ask, why does light have the specific speed it does in our universe? Why 299,792,458 meters per second and not some other value? The honest answer is, we don't know. It seems to be an arbitrary fact about our universe, like the mass of the electron or the strength of gravity. We can measure these constants, but our theories don't explain why they have the values they do, unless there are other universes with different values. This is the multiverse hypothesis, and it comes in many forms. The version relevant here is the landscape multiverse, derived from string theory. String theory, which attempts to unify all forces and particles into vibrating strings of energy, predicts an enormous number of possible universes, perhaps 10,500 different configurations, each with different physical laws and constants. In this landscape, light speed would vary from universe to universe. In some universes, light might move at twice the speed it does here. In others, 10 times slower. In most universes, the constants would be so different that atoms couldn't form, stars couldn't shine, and complexity couldn't arise. Those universes would be sterile and lifeless. We live in a universe where light speed is just right to allow chemistry, stars, galaxies, and ultimately, life. This is called the anthropic principle. We observe these particular values because we couldn't exist in universes with different values. It's a selection effect. We're sampling from only the universes capable of producing observers. But here's where it gets interesting. What if our universe isn't completely isolated from other universes? What if there are interfaces, boundary regions, or transition zones where the constants start to shift? Some cosmologists have speculated about cosmic domain, walls, boundaries between regions of space with different vacuum states, like the boundaries between frozen and liquid water. If our universe underwent a phase transition during its early moments, there might be domain walls left over, separating regions with slightly different physical laws. If you encountered such a domain wall, you'd cross from a region where light moves at one speed to a region where it moves at another. From your perspective, light would appear to accelerate or decelerate as it crossed the boundary. There's no evidence that such domain walls exist in our universe. If they did, we'd see discontinuities in the cosmic microwave background radiation or other large-scale anomalies. But the fact that our theories allow them is significant. It means variable light speed isn't forbidden by physics, just by the particular configuration of our universe. Now let me take this to its logical extreme. If the multiverse is real, and if different universes have wildly different physics, then somewhere in the landscape, there might be universes where light speed isn't constant, even within that universe. Universes where light accelerates naturally, without special engineering or extreme conditions. What would such a universe look like? For one thing, causality would be very different. Cause and effect might not have a strict order. Events might influence their own causes. Time travel might be commonplace. The past and future might be more fluid, less fixed. Life in such a universe would have evolved under completely different rules. Intelligence, if it arose, would think differently about time and causality than we do. They might see the past and future simultaneously. They might navigate through time as easily as we move through space. This sounds like wild speculation, but stick with me. There's a principle in physics called the principle of mediocrity, or Copernican principle, which says we shouldn't assume we're special or in a privileged position. Earth isn't the center of the solar system. The solar system isn't at the center of the galaxy. The galaxy isn't at the center of the universe. Applying this principle to the constants of physics, why should we assume our universe's light speed is typical? If the multiverse exists, we're probably not in an average universe. We're in one of the rare universes where complexity can exist. But that doesn't mean we're at an extreme. There might be other life-supporting universes with significantly different constants. If we could somehow send signals across the multiverse boundary through wormholes, quantum entanglement, or some other mechanism, we might be able to communicate with civilizations in universes with different light speeds. And that communication would teach us whether variable light speed is compatible with complex life. Here's a thought experiment. Imagine we detect an anomalous signal, a pattern of light that seems to violate our physics. It's moving faster than it should, carrying information in impossible ways. One explanation: it's a message from another universe, leaking through a boundary region where the laws are shifting. How would we recognize such a signal? It would look like noise, like a glitch in our instruments, like something that shouldn't exist. And that's exactly what we'd ignore in our data analysis. Scientists filter out anomalies all the time. We assume our equipment malfunctioned or our models need tweaking. But what if some of those anomalies are real? What if we're already seeing evidence of variable light speeds or multiverse leakage, but we're dismissing it because it doesn't fit our paradigm? This is the problem with revolutionary discoveries. They look like errors at first. Pulsars rapidly spinning neutron stars that pulse radio waves were initially called LGMs, little green men, because their signals were so regular they seemed artificial. Cosmic microwave background radiation was initially thought to be instrument noise. Plate tectonics was ridiculed for decades. Every major paradigm shift in science begins with someone taking seriously what everyone else dismisses as impossible. And right now, we're dismissing variable light speed because our current theories say it's constant. But theories change. Data forces them to. So here's my challenge to you. If you're a researcher, look at your data with fresh eyes. What anomalies have you seen that you explained away? What don't fit? What makes you uncomfortable? Maybe, just maybe, those are the signals we need to pay attention to. And if you're not a researcher, start thinking about how the world would be different if light could accelerate. What technologies would emerge? What questions would become answerable? How would society change? Because if this becomes real, if we discover that light speed is variable, your children or grandchildren will live in that transformed world. And the time to start preparing for it is now. Let's get practical. Forget the multiverse and black holes for a moment. If you wanted to test whether light could accelerate, what experiment would you do? I'm going to walk you through several proposals, some real, some speculative that could potentially detect variable light speed if it exists. Experiment 1. Ultra-precise atomic clock networks. Right now, the most accurate time measurement devices on Earth are optical lattice clocks, which are accurate to one part in YP. That means they would neither gain nor lose a second over 15 billion years, longer than the age of the universe. In 2021, physicist John Chiela in Colorado demonstrated that these clocks are so sensitive they can detect gravitational time dilation over height differences of just 1 millimeter. Raise the clock 1 millimeter, and time speeds up by a detectable amount because gravity is slightly weaker. Now, if light speed varied across space, perhaps due to subtle variations in vacuum energy or quantum foam, structure different clocks at different locations would drift relative to each other in ways that don't match gravitational time dilation predictions. By comparing a network of ultra-precise clocks around the world and in orbit, you could map out any spatial variations in light speed. The key is to look for patterns that can't be explained by known effects. If clocks in the southern hemisphere drift differently than clocks in the northern hemisphere, and the pattern aligns with the axis of evil in the cosmic microwave background I mentioned earlier, that would be evidence of anisotropic light propagation. Experiment 2. High-energy astrophysics. Every second, Earth is bombarded by cosmic rays particles, accelerated to nearly light speed by extreme cosmic events like supernova and active galactic nuclei. Some of these cosmic rays have energies exceeding YY electron volts, which is mind-bogglingly high. A single particle carrying the kinetic energy of a baseball thrown at 60 miles per hour, concentrated in something billions of times smaller than an atom. These ultra-high energy cosmic rays should interact with the cosmic microwave background radiation as they travel through space, losing energy in a process called the GZK cutoff, after Greisen, Zatspin, and Kuzmin, who predicted it in the 1960s. This means we shouldn't see cosmic rays from sources farther than about 50 million light years away if they have energies above a certain threshold. But we do. We detect ultra-high energy cosmic rays that seem to come from farther away. This is called the GZK paradox, and it's been puzzling astrophysicists for decades. One explanation may be light speed, and therefore the GZK energy threshold was different when these cosmic rays were created, allowing them to travel farther before interacting. If light speed decreases over cosmic time, particles created in the distant past would experience different interaction thresholds than particles created recently. Testing this would require detailed statistical analysis of cosmic ray energies, arrival directions, and distances to potential sources. It's the kind of puzzle that needs big data and sophisticated modeling, exactly the kind of thing modern astrophysics excels at. Experiment 3. Quantum vacuum engineering. This is where we get really speculative, but stick with me. In quantum field theory, the vacuum isn't empty. It's full of virtual particles, constantly popping in and out of existence. These quantum fluctuations have measurable effects, like the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force because there are fewer virtual particles between the plates than outside them. The properties of the quantum vacuum, its energy density, its fluctuation spectrum, determine the speed of light. Light propagates by exciting the electromagnetic field, and the quantum vacuum provides the medium, in a quantum sense, through which that excitation propagates. Now, what if you could manipulate the quantum vacuum? Create a region where the vacuum energy density is different, where the virtual particle spectrum is altered? In principle, this would change the local speed of light. How would you do this? One proposal involves using extremely intense lasers focused on a tiny region of space. At high enough intensities, the laser's electromagnetic field becomes so strong that it affects the quantum vacuum itself, potentially creating nonlinear effects where light interacts with light. In 2017, researchers at the Extreme Light Infrastructure in Europe began building lasers capable of reaching intensities of 1024 watts per square centimeter, high enough to probe these quantum vacuum effects. At such intensities, you might see light slowing down or speeding up as it passes through the focal region. Experiment 4. Gravitational wave plus light coincidence. I mentioned earlier that gravitational waves and light from the same event arrive at nearly the same time, confirming they travel at the same speed. But what if we looked at more subtle effects? When a gravitational wave passes through space, it stretches and compresses spacetime. This temporarily changes distances, but it might also temporarily change the properties of a vacuum, the quantum fields that determine light speed. If so, light passing through a gravitational wave might speed up or slow down slightly as the wave passes. This effect would be tiny, far too small to detect with current technology. But future gravitational wave detectors, like the space-based LISA laser interferometer space antenna, planned for the 2030s, might be sensitive enough. LISA will detect much lower frequency gravitational waves than LIGO, and these waves last longer, giving light more time to accumulate phase shifts as it travels through them. If you could correlate the arrival times and properties of light and gravitational waves from the same source with extreme precision, you might detect minuscule variations in light speed as a function of gravitational field strength. It would require analyzing hundreds of events, but it's doable. Experiment 5. Tabletop quantum optics. Not all tests require billion-dollar equipment. Some of the most profound discoveries in physics have come from clever tabletop experiments. In 2020, physicists proposed a scheme using quantum entanglement to test the constancy of light speed. Here's the idea. Create pairs of entangled photons which share quantum properties even when separated. Send one photon through a normal path and the other through a region where light speed might vary, like an ultra-cold atomic cloud or a nonlinear crystal with engineered properties. When the photons reach detectors, measure correlations in their quantum states. If light speed varied for one photon, but not the other, the entanglement would be affected in specific, predictable ways. By analyzing these correlations, you could infer whether light's speed changed along one path. This experiment is within reach of current technology. Universities with quantum optics labs could potentially build and run it. The challenge is distinguishing genuine light speed variation from other effects that also modify quantum states, like decoherence or dispersion. Here's the beautiful thing. Any one of these experiments, if it found positive results, would revolutionize physics overnight. And all of them are either running now or could be built within a decade. We're not talking about sci-fi scenarios centuries in the future. We're talking about real tests using real equipment that could answer this question within your lifetime. And that should excite you, because one of these experiments might, right now, be recording data that will change everything we know about reality. The answer might already be sitting in a hard drive somewhere, waiting for someone to notice it. Now we need to confront something deeply unsettling. If light speed can vary, if one of the fundamental constants of nature isn't actually constant, what does that say about reality itself? Throughout history, humans have searched for eternal truths. Plato spoke of perfect forms that exist beyond the physical world. Religions speak of unchanging divine laws. Even science, at its core, is a search for universal laws that apply everywhere and always. The speed of light has become one of our most cherished universal laws. It appears in the equations of relativity, quantum field theory, and cosmology. It's etched into the fabric of spacetime. It defines the structure of causality. We've built our entire physical worldview on the assumption that this number is fixed.